The purpose of this lab was to observe the motion of an object moving at a constant velocity without changing direction and apply Newton's second law to the data. This is the equation for Newton's second law. I will go deeper with this equation after all the data is collected. For this lab, I took a video of an exercise ball moving across the ground after I rolled it. I then inserted this video into Tracker to analyze it and collect data about the ball's motion. First off, I calibrated the length of the ball at the beginning of the roll. The measured diameter of the ball was 18 inches, which is 0.4572 meters. This calibration made the data match up with the actual size of the objects in the video. In the video, the ball is rolling from left to right. So I centered it on the x-axis. And the ball travels in the positive x direction. The starting position of the ball is not exactly at the origin, as you can see from this highlighted x value, but this is accounted for in the program written in Python. If I had changed the orientation of the axes, the ball would appear as if it was moving up, down, left, right, in, or out, but the velocity would still be the same. It would simply be in a different direction. As the ball rolled, I found each new position by finding the center of mass of the ball during that new frame. As this took place, Tracker created a fairly linear graph in the upper right-hand corner. The observed data for time and distance are in the bottom right-hand corner. I ignored the y values because they are approximately 0. I exported the x values and the time values into Excel and graphed them with the predicted values of constant velocity. We will view these in a bit. The predicted values were found using Newton's second law, which is shown here. This can be rearranged to be V final equals V initial plus the net force over mass times delta t. Because the ball was rolling at a constant velocity, the net force is assumed to be 0. Therefore, this makes V final equal to V initial for the computational model. The predicted values and computational model for the motion were found using VPython. I had to take a few things into account when editing the program. First of all, I made the initial position of the ball at vector 0.2200 because the ball did not start exactly at the origin. Next, the net force was made 0 because the ball is moving with constant velocity. Because the net force is 0, notice V initial is equal to V final when representing Newton's second law. This equation represents the displacement equation for constant velocity, which is R final equals R initial plus the average velocity times delta t. Here's the equation written out. The time vector is multiplied by the average velocity, which ends up being 1.943, and this was found by taking the average of the tracker data. The initial position was subtracted from the final position and divided by the total time. Here is the average velocity shown in our coding. Now we are going to run the module with time less than 1.248 seconds. The data was saved to a CSV file and graphed in Excel with the observed values. As you can see, the observed data is very close to the predicted data. Both are linear and the models fit well. The velocity for the observed data is 1.9433 meters per second, and the velocity for the predicted data is 1.943 meters per second. The percent error for the motion is 0.01%, which tells us the model fits extremely well and there were very few errors based on the data. A possible source of error could have resulted because the ball was not a perfect sphere. However, by choosing to use the first and last positions of the ball when finding the average velocity, the error is smaller and the motion is still depicted with constant velocity without an effect from the ball's shape. Because the percent error is so small and the computational model is a very precise and accurate representation of the observed motion in the video, it is clear that Newton's second law can be used to predict real-world scenarios of objects with constant velocity. However, as soon as an object begins accelerating, speeding up, or decelerating, slowing down, the model no longer is a linear fit.